Hello everyone, I'm Ashish Pandey. I'll be sharing my work on fuzzy engineered multi-cloud resource brokering for data-intensive applications on behalf of other authors as well. Dr. Prasad Kalyam, my colleague Zen Liu, and Dr. Dipti Joshi. Um, as you all know, we are living in a digital world where a lot of data is being generated every day, and we are trying to solve a problem where researchers or data scientists have a lot of data with them, and they have to analyze the data on cloud clusters or cyber resources in general. But we'll be focusing more on biological data, which is being generated from generation sequencing platforms. And we see here there's a researcher who wants to know some resources where they can he can run his data pipelines optimally, but because of lack of resources, he's confused on how to go through or navigate through the space of resource selection. So one option, the option which every researcher is having is to execute their pipelines on local servers, but there's a growth in cloud platforms throughout, and we all know AWS, Amazon Cloud, uh, Azure, and then Google Cloud platforms, which is gaining traction now more than ever. Apart from these cloud providers, which are more driven by economics, there are other resources which are funded by government, which are Genie, Jetstream, and Chameleon, which give lower cost but are used mostly for this kind of analytics or network problem solving. So given that we have so many resources, it's always a problem of access of which resource to pick, because each of these platforms has their own custom policies, and this is something which is very time consuming, and we want to solve this problem for the researchers so that they can focus on their pipeline or data analytics part. So the agenda of today's talk is I'll be going through the introduction, which will have problem sections, and the middleware is the section what we have developed. And then I'll talk about some bioinformatics workflows, and finally the evaluation of our middleware on those workflows, and then the conclusion. So the main problem which any user of these cloud resources has is how to pick resources so that the performance, agility, cost, and security metrics are fulfilled. And we are trying to design a middleware specifically to capture users requirement, which can fulfill these metrics while improving their pipelines performance on the platforms. So any workflow execution for a user or a researcher has to be taken care of in two ways. One is quantitative criteria of selection of resource for the workflow, and the other is qualitative criteria. In the quantitative one, there are specific needs of the workflow like CPU or RAM, or with qualitative, it's more towards what researchers want from the infrastructure, and which includes performance, agility, cost, and security of the solutions. So we went through some research areas where people have been trying to come up with models to to quantify the requirement from the user and convert it to resource allocation. One of these work is from um, Samia, who have been trying to quantify resource selection by characterizing the cloud resources. And they've used a fuzzy model for the evaluation of performance based on certain metrics of workload, hypervisors, and network devices. The other researcher, Chopra, has also been working on fuzzy logic techniques, and they have been using deep learning to create rules for these fuzzy inference engines, and their main metric or parameters were priority, age, or execution time of the process which has to be executed. And the third work, which has been uh, a guiding paper for us to implement our model as well, has been from Rizvi, where they have been trying to use fuzzy inference engine to evaluate security of cloud service providers. And for that, they have considered multiple sub factors for security, and they basically collect data from users and assess their perspective with these sub factors for security. So now in our work, we are trying to develop a middleware which will be trying to capture all four factors: performance, agility, cost, and security. And we have again used fuzzy inference model, which will be considering multiple sub-factors for all these uh, criteria of performance, agility, cost, and security. We do benchmark these metrics for three distinct cloud providers and show that fuzzy inference can actually assess users' requirement and come up with optimal platform for their workflows to execute. So this here is our middleware architecture. If you see here, the users has an option of giving the requirement in terms of quantitative measures, and then we have developed FIS, which is fuzzy inference system, which collects data for qualitative assessment of what user want from their cyber resources. And based on these criteria, rule engines or rule knowledge bases are developed for fuzzy inference. And if you see on the right, the fuzzy inference engine gives back different ratios for the cloud, and it basically suggests the optimizer which cloud to pick for generation of cloud template for the workflows of the user. If we dig deep in the fuzzy inference, we have made a multi-hierarchy fuzzy inference model, where the first level, we collect data from users in terms of uh, different questions, and all these questions basically guide or are actually manifestation of sub-factors of packs. And at the first level, we try to assess what are the packs benchmarking for different CSPs for the user. And at the second hierarchy, we try to come up with which cloud should work well for the user, given that a packs has been generated from the lower level. So once the packs has been generated from the lower level, and a ratio of AWS, Genio, and GCP has been decided by the fuzzy inference model. This ratio is passed on to our ILP optimizer, which then creates cloud template solutions by considering those clouds favorably, which is having a higher ratio from the fuzzy inference model, which is governed by this MP factor here. And there are multiple templates created. We use these templates to run the workflow, and the execution time of those workflows decide how well our fuzzy inference model has performed. So for fuzzy inference model, we have used a Gaussian membership function, where we have divided users' answers into five distinct categories. That is exceptional, great, average, poor, and bad. And they all follow a Gaussian model. And we apply this Gaussian model for each of these metrics of packs at two distinct levels. The first level, we get how the users is rating different clouds in terms of these packs factors. If you see here, the sample example is the packs is in ratio of 80, 70, 60, and 30. Based on these inputs, the second set of input gives out that the user needs Genie up to 60% and the AWS for 40%. We used a centroid model for defuzzification, and after this defuzzification has been done, This is passed to our ILP optimizer, which creates the templates. The knowledge base which we used here is created by the user's input itself from FIS, where they can suggest which AWS, which cloud to use when certain criteria of packs has been met. And these rules are dynamic. The users can create as many as they actually want to create, and the more rules there are in the fuzzy inference model, the better or more accurate model will be generated. We applied these cloud templates on 3 distinct workflows from bioinformatics. These are FastQC, RNA-seq, and PGen, and they are ordered in increasing order of complexity or time taken. And we use multiple configuration of resources to execute these workflows. And the user is asked to first answer very specific questions to find packs, and then on the next step to find which cloud to choose for them. And once the cloud has been chosen, these quantitative requirements on the right hand side is passed to ILP optimizers to get exact cloud templates on which these workflows will be executed. Here's an example of RNA-seq workflows. These are basically directed acyclic graphs where there are parallel threads running at different stages. If you see bow tie, top hat, cufflinks, cuff compare, and cuff diff, these are all tools which execute at different stages of the workflow execution. And we run these workflows on the assigned cloud templates, which are coming from our fuzzy inference and ILP optimizer, and then compare how these workflows improve over time when the fuzzy inference or fuzzy engineering is applied. We create the testbed by using a set of software tools, namely MATLAB. So MATLAB was used for creating the fuzzy inference engine. Then Pegasus was used to control the workflow management. Condor was used to create clusters on these clouds. And PyGladin was used to integrate Pegasus and Condor with the cluster. Cyverse is where we stage the data for the workflows. And iRods is a tool to connect the data and the workflow on the cluster. For ILP optimization, we use iLog Cplex Optimization Studio from IBM. And the clouds which were used for our experiments were from Genie, MU Local Data Center, and Amazon Web Services. So this is a complete integration of all the tools along with our fuzzy inference engine. The users are asked certain questions based on these sub-factors on the right-hand side, like flexibility, capacity, compute cost, reliability, encryption. A PAX metric is generated on the second step of the fuzzy inference, and then it suggests the best CSP for those users. And then we apply ILP optimizer, and the templates are created and sent to our DAG manager, which is the SD Condor, which executes the workflows which is passed from Pegasus WMS. And once the results are out, we can actually measure the time it took for the workflows to execute. So this step was performed numerously around 10 times to create or generate data for each of the workflows at different configurations to find if the fuzzy inference model improved the workflow's performance. So we used 2 evaluation criteria. One was the evaluation of fuzzy model itself, and the second one was how this on-time FLC model has improved the workflow's performance. In the first step, when we evaluate the fuzzy model, we have measured performance, agility, and cost of different cloud providers in perspective of an expert user. So we ask iteratively a number of questions from the users to rate different all these these 3 distinct cloud providers in terms of the sub factors. and all the results are then normalized from 1 to 100 and are passed into fuzzy inference model at the first stage. At the second stage, when the results come, it's again normalized from 1 to 100 and passed to the second stage. And at the third stage, we get the ratio of which cloud is performing better for the user. So these are the results of the first stage, where we are trying to benchmark performance for these three distinct clouds. And we used 1,000 different CSU users, and we simulated these 1,000 users, which are picking randomly uh, their perspective toward these subdomains. And if you see, AWS has performed well in terms of performance, which is around 85%, compared to Genie, which is 75, and then MU was 55. So this suggests that the user is more inclined toward AWS when performance matters most for them. Similarly, for agility and cost, for agility, again, AWS performs well, and Genie and MU are on the same level at around 65 or 55. For cost, Genie outperforms MU and AWS because Genie is the most uh, cost-effective solution, because it does not charge users too much to run their workflows on top of it. While AWS is the most costliest option here, so it goes down in the benchmarks. So this suggests that the first level of hierarchy from the fuzzy inference model works well, and it can benchmark different cloud providers in respect of users' preferences. The second evaluation, we executed all the three workflows, which are in increasing order of complexity, 10 times, and we try to find how much time it took for the workflows to execute. Uh, so in so we compare our on-time FLC, which is having both uh, our ILP optimizer engine as well as fuzzy engineered inference model, and we compare it against only ILP optimizer engine where there is no fuzzy inference model. And we found that with fuzzy inference model, the cloud templates which were generated were giving better results when the workflows were running on them. And if you see on the figure, these results are average values. Uh, so we performed the experiment 10 times, and on an average, we found the workflows were having a better time of time of execution. And interestingly, the workflows which are larger in size have better improvement compared to smaller workflows. That is because the margin of error when the workflows run itself is very large when smaller workflows run, and that's why the fuzzy engineering model doesn't perform well in those cases. So with our middleware, we have um, developed a framework with on-time FLC, which can capture users' requirement and pass it on to our ILP optimizer, which suggests good cloud templates to execute the workflows. And we also found that our framework is efficient in capturing all the users' requirement in terms of PAX metric, and hence we can add more uh, cloud providers data inside this for the inference model and make it more generic, and thus more providers can be added inside the framework. For the future work, we'll be trying to leverage machine learning to learn some of these rules and create better, more robust rules for the fuzzy inference engine, so that it can improve the PAX metrics learning performance of fuzzy even more. Thank you for your attention, and I look forward to seeing you all in our conference presentations.